preliminarily, but oh, we have three. Okay, perfect. You like precision. Okay, so it's my very great pleasure to introduce Eryn Cangi, who is, in fact, I didn't ask you how to pronounce your name. I hope that's close.
That's the most common one I get. It's Cangi, but
Cangi,
don't worry,
okay, all right,
most people don't
thank
get it right.
Let's get this right. So Eryn Cangi, who is visiting us from the Laboratory for Atmospheric and Space Physics, so LASP at UC Colorado. So she started out her career, she is in fact a Pacific Northwestie, so she got her Bachelor of Science from the University of Oregon. She then went on to UC Boulder to do her PhD. She's now a research scientist at LASP in Colorado. She is an expert on atmospheric escape from terrestrial planetary atmospheres, and she has been working with the MAVEN team on that. So ask her about Mars. I'm sure hear about Mars today. She has very broad interests, but they're kind of centered around atmospheres. So she's interested in, of course, Martian atmospheric escape, but also atmospheric dynamics, terrestrial planetary evolution, climates, surface interaction between atmosphere and surface, remote sensing, and planetary habitability. And so with that suite of interests, I will now introduce you, and I will now hand you over to Eryn, who will tell us about her research in atmospheric escape.
Great, thanks for that intro.
Thank you.
So I'm Eryn. I am at LASP NCU Boulder, and Vicki was saying UC, for some reason, we say CU.
Sorry, I shouldn't have said that.
No, it's fine. It's something that always confuses people, and I think it's really just to distinguish us from the UC system. Sorry, what?
Literally blame California.
Yeah.
These are the UC schools, so that's why.
You must also be from Oregon or Washington.
Austin. But close enough.
Sorry.
So first in Colorado, so it's good.
Yeah. Okay. So let's go ahead and get started. And I do not want to annotate. I guess I'll just touch the mouse, not the arrow keys. So a quick outline, I'll go through some background on atmospheric escape and Mars and Venus, since I know that we're a mixed group here who are all interested in astrobio. I'll cover the methods briefly, which for me means photochemical modeling and UV spectroscopy, ultraviolet spectroscopy on the MAVEN mission. And then I'll have a little bit about Mars, covering a new mystery that has recently occurred that we've been working on, which is a detection of water vapor in the thermosphere, the high atmosphere of Mars. Then I'll talk about Venus. So this is about a paper we released last year, where we revealed a new mechanism driving hydrogen loss. And that has some implications for past oceans and habitability. And then I'll sort of wrap up talking about exoplanet things from my perspective as a solar system scientist. Okay, sorry about that annotate thing. I'm not sure how to make that go away, but we'll do our best. So I've already got a little bit of an intro from Vicki. Thank you very much for that. I'll fill in a couple things here. Indeed, I went to University of Oregon. I have 2 degrees from there, theater and physics. So if you're curious about what the heck happened there, ask me offline. Happy to talk about it. My thesis for the PhD was about the variability of fractionation of deuterium and hydrogen in the Martian atmosphere. And I worked with Mike Chaffin and Nick Schneider, who are also part of the MAVEN mission. And just to say it outright, so we're all on the same page, that stands for Mars Atmosphere and Volatile Evolution mission. So we study the upper atmosphere of Mars and the escape. And then I have continued at LASP because, why leave a really awesome active mission like MAVEN? So I did a postdoc there, but it's weird because we're not really called postdocs at LASP. And I just promoted to not postdoc. So 1 level up in research scientist. So that's my situation. I went to CU because I was really interested in atmospheres, as you might guess. I was definitely sure that I wanted nothing to do with planetary surfaces when I started grad school. But then when I got to CU, I started talking to geologists and I was like, oh no, this is actually really interesting, especially if you care about planetary evolution. You can find out a lot about that in the rock records. So there's a picture of me enjoying rocks and atmospheres in Utah, which is a great Mars analog. So I've had a lot of fun going around the West, checking out all the parks and thinking about planets. Okay, so there's lots of reasons to care about atmospheres, even if you're not an atmospheres person. If you're an interiors person, atmospheres are formed partially, at least, by outgassing or volcanic activity. That's one way we can form these secondary atmospheres. Wrong direction, sorry. Atmospheres can also shape the surfaces of planets, such as through aeolian processes like dune formation. So here's one of my favorite pictures at Great Sand Dunes in Colorado, where we have a little isolated pocket of dunes surrounded by mountains and farmland. Since we're all astrobiologists or astrobiology interested people here, you probably are also wanting to know, are there aliens? It's definitely a big question for me. I'd love to know the answer. If there are aliens out there, some of them probably need atmospheres, maybe not our tardigrade friends, but maybe more like megafauna, so to speak, may need atmospheres to survive. So that's something to think about. And of course, if we want to know if the planet has an atmosphere, we have to think about how did it get there? Has it escaped? Is it still around? So many of you might know this plot from a paper by Zonley and Catling, which is from their cosmic shoreline idea of like whether planets have an atmosphere or not. So if you plot the insolation of the star relative to the escape velocity, you seem to form this sort of nice line where below this line, planets will tend to have atmospheres and above they won't. But as we'll see, there's lots more that goes into this picture. Here's another complicated figure showing you how much goes into it. I really like this summary figure of different atmospheric escape processes by Guillaume Gronoff, because it shows lots of different things that can occur on different types of planets and how they overlap. So if we're thinking about like very young planets or many exoplanets with extended young hydrogen atmospheres, a lot of that escape tends to fall into the hydrodynamic escape category, which I'll talk a little bit about when I get to Venus. But once you've removed a primary atmosphere and maybe you formed a secondary atmosphere through outgassing or maybe even volatile delivery from impacts, you can lose it in many other different ways as well, which are sort of captured on this figure. There's a whole lot here, like each one of these could be its own talk. I'm not going to go into every single one. Lots of this has been covered by my colleagues on the Maven mission. My work has mostly been focusing on thermal genes escape of hydrogen and deuterium and also photochemical escape, which I might call that non-thermal escape in this talk. And non-thermal escape is really like a big bucket that contains a lot of different processes. But if I say it, I'm talking about photochemical escape, which I will define shortly, so don't worry. Okay, so before we go into that, I got to tell you all a little bit about deuterium and hydrogen. So this is how we know that planets have lost water, and this is what a lot of my work has been on. So on a planet such as Mars or Venus, because the same process applies, you might have hydrogen atoms and you might have deuterium atoms, which are the heavy isotope of hydrogen. On these two planets, maybe not all rocky exoplanets, but at least on Mars and Venus, the main reservoir for these atoms is the water molecule in the atmosphere. When those are in the vapor form, they can absorb incoming sunlight and then dissociate into their constituent atoms. Now, there's a mass difference between H and D, and it's really like the biggest mass difference you can get between isotopes because, of course, the mass of hydrogen is just one on the scale of masses. So those can then undergo escape, but they'll do it at different relative rates. So this has the function of increasing the amount of deuterium relative to hydrogen that remains on the planet. When those atoms recombine into molecules again, this effectively changes the ratio of D to H in the water molecule, which is how we usually talk about it. So if you can assume a planet began with an Earth-like water abundance and D to H ratio, which is pretty good for Mars and Venus, then you can say that an enhanced D to H ratio tells us the planet has lost water over its history. You can also think about the D to H ratio in the escaping atoms, and this is called D to H fractionation or fractionation factor. And a lot of my work during my thesis was on that, but I'm actually not going to talk about it too much in this talk, but if you are curious, feel free to ask about it. Okay, so now that we've thought about the fact that D and H can escape differently, let's think about how they escape. So thermal genes escape is the main vector for hydrogen loss on Mars, but it's not actually that efficient for deuterium. So the way that this works is that if you've got a whole bunch of atoms in the atmosphere of a planet, they're going to have their velocities described by some Maxwell-Boltzmann distribution, which I'm showing down here. Most of those atoms will fall below escape velocity in this gray region, so they won't escape, they'll be retained on the planet. But some of them will have their velocities in the high energy tail and they'll be able to escape to space. And this is just due to their like natural thermal motions. In contrast to Mars, this is not very efficient at Venus at all. So that's when non-thermal mechanisms will come into play. And the ones I'm going to talk about in this talk are, as I said, mostly photochemical escape. So like I said, non-thermal escape is this big bucket of other processes. So thermal genes escape is more about when you have local thermodynamic equilibrium, you can use this distribution to describe the velocities. For non-thermal escape processes, it doesn't apply. These atoms are gaining extra energy in some other format, some other way. So some of those processes include ionospheric chemistry, as shown here. It could be ion neutral chemistry, dissociative recombination of an ion and electron, or even photolysis, aka dissociation of a molecule due to sunlight. All of these different processes can remove H&D from both Mars and Venus, and especially Venus because thermal escape is not efficient there just due to the higher gravity. So we know that both Mars and Venus used to have a bunch of water on them. On Mars, we know it was liquid because we can look at the surface and send rovers to it, which is awesome. Venus, it's trickier, right? Because it's very hard to go to the surface of Venus and also to look at it. When we observe their globally average D to H ratios in the atmosphere, this is what we see. Mars has an enhancement about 5 times the Earth value, and Venus is about 120 times. And actually, that number is a little bit squirrely depending on where in the atmosphere you're looking. But this tells us that there's been quite a lot of water loss from both of these planets. We do need to have a way to talk about how much water that is. So I'm going to give you a quick little units definition. We usually talk about it in something called global equivalent layer, or some people call it gel. So this is if you took all of the water on the planet, no matter what phase it's in, ice, vapor, liquid if you got it, and spread it out on the surface, the depth of that layer is your gel. So it can be in centimeters, kilometers, or meters, as you see there on the chart for these 3 different planets. And you'll notice that Mars is sort of like a middling amount between Earth and Venus today is very, very, very dry. So that'll come up again in the Venus section. Okay, so let's move on to some methods. And for me, that means photochemical modeling and UV spectroscopy. So the work I did during my PhD was pretty much mostly photochemical modeling, because modeling sometimes takes a really long time to get right, and it can be kind of difficult in that way. So during my PhD, I developed a photochemical model, which we have named Blue Jay. We have a bird theme going on in our group. We have other models too with other bird names. These are some of the main cast of characters who are working on it. There's me, my PhD advisor, Mike, and our past postdoc, Bethan, who's now returned to the UK for a job at home, and our current postdoc, KP. Okay, so this is a little primer if you've never heard of photochemical modeling before, or if you're not quite sure. These types of models are one-dimensional models. So our only coordinate is altitude, and it's meant to represent sort of a global average of the planet. It takes a variety of different inputs. This is not all of them. These are some of the main ones. We can change the atmospheric temperature, how much we think is there of like the main constituents of the atmosphere, the initial densities. We can change the solar flux that's coming in as a function of wavelength, and also, of course, chemical reactions. So these models solve coupled stiff differential equations of chemistry, which maybe some of you are now like, ooh, chemistry. And that was definitely me when I started. These models will run forward in time, and people tend to usually run them to equilibrium. So when these production and loss rates through chemistry and transport balance, but we can also look how they change over smaller ranges of time. The output looks something like this. You've got the species density at each altitude. And this might seem a little non-intuitive to some of you, but for some reason, just when we do photochemical modeling of atmospheres, we put the altitude on the y-coordinate so we can like kind of see, like this is what the vertical profile looks like, so to speak. From that output, we can compute all of the escaping hot hydrogen or deuterium that's produced by the different chemical reactions. We can also do the thermal escape, although I don't have that here on the slide. That gives us the total global escape rate, and from there we can figure out the integrated water loss from the planet and other variations that might occur in D to H ratio of different species. Okay, now for something completely different, MAVEN. So I'll give you a little bit of a primer about our mission. So MAVEN is currently at Mars. We just celebrated 10 years at Mars, which is super exciting. Thank you. MAVEN is part of a program that's no longer solicited called the Mars Scout program. And I'm not even totally sure what the cost cap was. But since it's within the inner solar system and had a decent cost cap, I want to say like a couple $100 million. We have a lot of instruments on MAVEN. I think I've got them all here. And I'm not even going to talk about most of these, but with all of these different instruments, we can study many, many, many different things about the atmosphere of Mars. Composition, temperatures, waves and tides, escape, solar wind interactions, all kinds of fluxes one way or another. The ones I'm going to focus on in this talk are from the imaging ultraviolet spectrograph, which allows us to get the Lyman alpha emission from hydrogen and deuterium. And that lets us really probe this question of escape and water loss at Mars. Sadly, there is no MAVEN for Venus. Venus has not had a lot of missions going on, but luckily there will be new missions soon, which is very exciting. Just a little bit more about IUVS. It is a UV spectrograph, so it can look across the ultraviolet spectrum and get lots of different emissions up here. We have two modes, a standard resolution mode and a high resolution Echelle mode, and it's the Echelle mode that lets us get the HMD Lyman alpha over here on the left in red. For those of you who think about resolving power, we have a resolving power of about 14,500 in the Echelle mode. Okay, so with those methods in mind, we're going to go on to the Mars part of the talk. So this is a new piece of work I did with my colleague Mike Stevens, who was previously at the Naval Research Lab, now is at a private institute called CPI. And Mike used the standard resolution mode of IUVS to detect some water in the thermosphere of Mars during the perihelion season. So just to orient you, perihelion season on Mars is when Mars is closest to the sun, and Mars has a fairly eccentric orbit. So lots is happening at this time of the year. It's also the southern summer region, or sorry, season. So this is when we get a lot of dust activity on Mars. The atmosphere is heating up, things are getting kind of chaotic. So lots is going on. And then for the thermosphere of Mars, if you're unfamiliar, this is basically everything about 100 kilometers in the atmosphere. So we don't have the same type of temperature structure as Earth on Mars. We just have this simple adiabatic lower atmosphere, a cool mesosphere, and then the thermosphere where the UV heating is very effective. So the water vapor was detected up here, which is surprising for reasons I will explain. So how this works is in the standard resolution mode of IUVS, we can observe what's called OH prompt emission. And this emission occurs through like a multi-step process. So when we have water in the atmosphere of Mars, it can dissociate, like I showed you before. It can produce these hydrogen atoms and then the excited hydroxyl molecule here, OH star in this case. Then that excited state of OH can decay, producing ground state OH and a photon, which emits in roughly this range here. And this is the emission that IUVS sees. And I'm showing you that that emission in the middle panel. So the top panel is the total spectrum, and then we've subtracted out some other stuff, which I've swept under the rug. And we have this OH prompt emission, and then there's also an OH fluorescence emission as well. From this emission, we can sort of go back through this process using math that I'm also going to sweep under the rug and back out how much water must have been there to produce this emission that we've seen with IUVS. So just to back up a little bit, we already knew that water was available in the upper altitudes of the atmosphere of Mars during this season. That was not the surprising part. So I'm showing here two plots from two different papers. The first is on the left is from paper by Nick Heavens. And this is showing the water abundance at different altitudes over the Mars year. If you're not a Martian, these numbers here are solar longitude or LSBS. It's really just like a timeline of the year. So southern summer is in the latter half of these numbers. And you can see here that there's like a good amount of water up to about 50 kilometers for most of the year when we have data. And then once we get to this dust storm season, when we see a global dust storm that happened in March of 28, that water like really jumps up and almost doubles its height in the atmosphere up to about 80 kilometers. The second plot on the right is from a paper by my colleague John Clark and a bunch of us on IUVS, also showing the Mars year on the x-axis, but now it's the H escape on the vertical axis, and each color is a different Mars year. So you can see that at the same time is reaching high altitudes, the H escape is increasing by about an order of magnitude. And I thought I used to have a little piece of text, but I guess I don't. It's an order of magnitude. Check out the y-axis on the plot. So, okay, we expected water in the atmosphere. We expected an H escape increase. We did not expect it to see it as high up as we did. So on the previous slide, it was up to about like 80 kilometers. We had this observation from IUVS up to 140 kilometers, which is really surprising. And if you're not sure why, think back to this temperature plot, or I'll just show it to you. The temperature gets quite cold there in the middle atmosphere around 100 K, and it's kind of hard to like convert based on the pressure of Mars. But I'll just tell you, you usually don't expect water to get much higher than that because it's too cold. It'll just condense out into the ice phase. So the fact that we saw it here is very surprising. And this is the point at which Mike Stevens came to me and said, hey, Eryn, can you take this data, put it into your model and see if it produces the same result? So Mike went from the OH emissions, so here he's backed out the density, and then the derived water abundance on the left. So he wanted me to put the water into the model, let it evolve chemically, and see if it produced a similar amount of OH as was implied from the emissions. Okay, that's what I just said. So I said, yeah, I could probably do that. I gave it a shot. We also took in like other data that was happening at the same time, like the temperature structure and the CO2 density. And the results are shown here. So again, the black is the data from IAVS and the red is the model output at different times after the water was introduced. And you can see that in this dotted line, after about a minute after introduction, the OH that's produced is like kind of close to what we saw in the data. It's not perfect. There's probably a little bit of discrepancy due to other model assumptions, but we were very surprised that this actually did line up fairly decently. And after about half of the day, about 13 hours, both of these vertical profiles have sort of relaxed to their more nominal values. So that was really interesting. We tried a lot of different things to try to falsify this result because we still were not quite sure how this water could be up there, but we couldn't make it go away. So we went ahead and published it. After that, we decided to look at how this affects the H escape. So on a previous slide, I showed how there's like an order of magnitude variation of H escape throughout the Martian year. And this plot here is showing the model results computing the H escape flux as a result of different scenarios where we've got this water in the thermosphere. So the black line is without any extra water, just sort of a nominal model case. The red line is a composite of a whole bunch of different observations we took with IAVS, and then the blue line is one particular observation where we saw a huge amount of water in the thermosphere. And this will induce an H escape, a change to the H escape on the order of about 2 to 5 times, which is pretty good considering like the normal seasonal variation is a factor of 10, this is a factor of 2 to 5. And we looked at this process for just one Mars season to see sort of a shorter time frame than running it all the way to equilibrium. Some work I'm doing right now to follow up on this is to look at the Lyman alpha emissions of H and D from IAVS from the shell mode. So all of that stuff I just talked about was the standard resolution mode. So we're trying now to come up with ways to independently verify this result by looking at different data sets. So if that water is up there in the thermosphere, it should dissociate and produce these H and D atoms. You can then look at their emission and the Lyman alpha emission to see if you can see any tracer of this behavior. The H and Lyman alpha emissions at Mars are optically thick, which means it's not very easy to go from a brightness that we detect with the instrument to a density. But you can do that with the deuterium because those emissions are not optically thick. So that's what I'm focusing on here. So I've grayed out the H for you. So this is 2 different times of year, and I've just plotted a whole bunch of different limb profiles that's like looking across the limb of the planet. So like across the atmosphere. And you would expect that at the time when you see this water in the thermosphere, you should see a little bump in the deuterium as well. And I think you can probably see, we do see that here during Southern Hemisphere summer at the same time. But then at the opposite half of the year, when we don't see that water in the atmosphere, the profile is fairly flat. So this is looking fairly promising. I'm working on writing this up now. And we also have developed some new observing modes with Maven to try to get at this problem other ways. I have backup slides on that. Ask me if you like. I'm going to skip it for time for now. Okay, so quick summary for Mars. We've detected water in the thermosphere very high up during southern summer in a place we didn't expect it. This is very interesting because even though we know a lot about Mars already, we have a lot of missions there, we have a lot of data, and the atmosphere is like comparatively simple versus Earth. We still have a lot that we don't understand about it and how it's different cycles like the dust cycle and the water cycle connect. This atomic H and D emission can be a useful tracer for water, but you have to be able to resolve them. At Mars, not so bad because it's so close to us, we can send a mission there. For faraway exoplanets, it might get a little bit more difficult, but I'm not an expert on like space telescope use, so perhaps it's not so bad, I don't know. I know Hubble Space Telescope can do it. So maybe there's an opportunity there as well. And again, there's like a huge variation at Mars due to the seasonal variations. And then the dust storms, which enable the heating that drives that water up into the atmosphere. And also orbital parameters, which I didn't really mention, but have that eccentricity that makes the seasons so different at Mars. There's more actually that I'll go into in the last part of the talk also. But for now, we're going to move on to Venus. Okay, so this is about a paper that we published last year. I think it came out the first day of AbSciCon, which was very exciting. So we got to do a little press conference about it and drum up the result for everyone. So this sort of came out of the work I did from my PhD in developing this photochemical model for Mars. Sort of as that was wrapping up, I realized that, the upper atmospheres of these planets are so similar. I wonder if some of the stuff that we found could also apply to Venus. And spoiler alert, it did. So that's very exciting. We had a local artist work up this mock-up cover for us for the publication, but sadly it was not selected. So you can just enjoy it here. Secretly, I wasn't the biggest fan because I think this looks like a golden snitch from Harry Potter, and I thought that was kind of confusing. But I think maybe I'm the only one who has thought that so far that I've said this to. It is a beautiful picture, though, not to denigrate the artist, of course. Okay, so we're starting in on this decade of Venus, right? There's new Venus missions planned, which I'm showing here on the bottom. Da Vinci, Envision, Veritas. These are all going to transform our understanding of the lower atmosphere, the surface processes, and some of the middle atmosphere, which is great because if we're also interested in exoplanets, it's expected that there's a lot of different exoplanets that are going to be Venus analogs, up to like 45% of the exoplanets around sun-like stars. So definitely worth studying Venus, and even us Martians are like cheering for Venus. So we're very excited. Okay, so thinking about the past of Venus, we know it has a much thicker atmosphere today. It's lost a lot of water, like I said in the beginning. And some of that loss of H early in its history was likely hydrodynamic. So if you have a lot of water available in an atmosphere, whether it's liquid on the surface or creating steam, that will tend to release a lot of H2 and H through dissociation processes. Now, some of us may know the H2 molecule is actually kind of a decent greenhouse gas when you get high concentrations of it, but it's a terrible radiator because it's this diatomic molecule. So it's not very good at cooling. So the only recourse a planet has to balance the incoming and outgoing radiation is, in this case, to undergo hydrodynamic loss when hydrogen sort of flows out as this nice smooth river into space. So this plot is showing how that relates to the water mixing ratio near the cold trap. So all of the hydrodynamic loss is happening basically over here to the right. And once you get to about 10 to the -3 mixing ratio, that process starts to shut down. And you take over, it's thermal loss that starts to take over, or non-thermal processes. In Venus's case, mostly non-thermal, since thermal is not super effective due to the gravity. We don't have a lot of certainty around how long this process takes. It could take a couple billion years to lose up to an Earth's ocean of water. And like I said, when you start to remove most of that water and you get down to a middling amount, the process of hydrodynamic loss starts to shut off. And then you have a little bit of water left, somewhere around 10 to 100 meters global equivalent layer, and then you've got to come up with a different way to remove that extra water. So on Venus, I've said it a couple times, that's most likely non-thermal processes. So hydrodynamic escape gets us down to this 10 to 100 meters gel layer. But like I said in the beginning, Venus is very, very dry today. We only have 3 centimeters global equivalent layer. So it's non-thermal processes that will probably take us most of the way. Until recently, the main process that people expected was doing this work to remove the extra water was this resonant charge exchange reaction, where you just switch a charge on a couple hydrogen atoms, and then you have a hot neutral atom, which is able to escape. The issue with this is that it doesn't really get you all of the way to removing this extra water. So this plot is showing the water inventory of Venus, not necessarily to scale. And then the x-axis is just time. So if Venus had Earth-like oceans early in its history, those could have persisted for some amount of time. It's also entirely possible that oceans never condense, so that's a different scenario. But either way, hydrodynamic loss will take a certain amount of time here. and get you down to this amount of water remaining. But then this resonant charge exchange is only really able to remove water down to about 26 centimeters left, but this is more than we see today. So there was there's something going on here that was telling us this wasn't quite sufficient. So using our photochemical model that we developed at Mars, we were able to investigate the chemistry of the ionosphere and the non-thermal loss processes. And we identified this new mechanism that hadn't been talked about in the literature before, HCl plus dissociative recombination. So this is recombination of an electron with the ion HCl plus, which on Venus is a terminal ion. That just means it's very likely to form based on the chemistry and it's hard to destroy. So this is like the main way we destroy that molecule. And it turns out to be very good at producing hydrogen and deuterium that are able to escape. So this plot is showing the production rate of these escaping atoms over altitude. And then the lines here are just color coded to these reaction labels. I know it's kind of a spaghetti plot. So just focus here on the red one, which is that mechanism I was talking about. We can then go ahead and integrate these profiles over altitude to get a total amount of escape at the top of the atmosphere. And that's this portion of the plot here. So now we can see that in comparison to the resonant charge exchange in pink, this, oh my God, it's so long to say. I tend to call it HCl plus DR. So this DR mechanism is actually about an order of magnitude stronger at removing hydrogen than the resonant charge exchange, and about a factor of 2 stronger than all the rest of the mechanisms put together. So this was an exciting result that we were like, wait, is this the case? This hasn't been in the literature. Nobody's talked about this. And you may have once heard the statement, all models are wrong, but some are useful. So of course we wanted to check this, like maybe there's something wrong with the model, maybe we've missed something. So we were able to go back and look at some data from Pioneer Venus, which did not measure the HCl plus molecule at all, because they had to pre-select the mass channels that would be measured with a mass spectrometer before flight. But it did measure these other molecules that produce HCl plus through chemistry. So that includes CO2 and hydrogen and their positive ions here. And by using the densities of those from PBO, along with what we know about the chemistry, we can come up with the amount that's being produced of HCl plus. And then as long as you believe that the atmosphere is relatively in photochemical equilibrium, that all of these HCl plus molecules will eventually lead to an escaping hydrogen, then you can back out the expected loss rate of hydrogen from this mechanism from the data. Excuse me, I'll take a drink here real quick. This turns out to be a pretty good assumption. And if you look at this final H production rate at day and night, a middle value between these lines up pretty well with our model, which reached a value of about 10 centimeter cube per second. This may not seem totally the same, but remember that the photochemical model is 1D. It's meant to represent a planetary average. And Venus has a pretty strong dichotomy because of how slowly it rotates. And there's actually a little bit of a hydrogen bulge on the night side, which we also see here in the data. So this actually lines up pretty well. So with that, we were able to put this out into the community for them to pick it apart. So this has some implications for on Venus in its history. And basically, if the escape of H today is faster than we thought, that means water could have hung around on Venus for longer, which may seem, you may be like, wait, huh? And the way to think about it is if you are going to the airport, you can stay at home comfortable on your couch much longer if you just drive way faster when you're actually on your way to the airport. If you don't like this analogy, that's fine. I didn't make it. That's Mike's analogy. You can blame him. But if it helps you, then excellent. Yeah, so this means that the water could have been stable on Venus for longer early in its history, whether or not you think it was in the ocean format. If you like the theory that it was, then those oceans could have hung around longer, could have enabled more habitable conditions. If you don't like that theory, totally fair. This has the implication of doubling the supply of water to the atmosphere in a steady state scenario due to outgassing or impact delivery. And then this table, we've just compared some of our, we've compared our rate of H loss from this mechanism to previous works. The takeaway here is just that it's about doubled the previous estimates, which I already said. There's still a lot of uncertainties about this though, especially since we don't have a ton of data on Venus of the upper atmosphere. Fortunately, we do have these new missions coming up. Like I've mentioned, these are going to focus on the middle atmosphere, the lower atmosphere, the surface, the cloud layer, but there's not a lot of focus that's going to be on the upper atmosphere. And this is tricky because we use these D to H ratios to understand the loss of water from the planet, but you can actually still have a lot of uncertainty if you don't understand the escape rate. So on this plot, we're showing again over time and then the D to H ratio on the vertical axis. Sorry, this V SMAU just means the number that it is on Earth. I forgot to define that. But you can get a very similar effect between like these blue and red lines. At the present day, you can get a similar D to H ratio, but with very different histories and different loss rates if you just change this fractionation, which is again, the relative escape of DNH by just a little tiny bit from 0.15 to 0.13. So in order to understand this D to H ratio and what it means for the history of water on Venus, we would really like to ideally understand the escape rates at the top of the atmosphere, just as well as we understand them at Mars through missions like MAVEN and all the modeling work that people have done. So I'm working a little bit on expanding this with Mike and our team. So right now I have an undergraduate, Simon Carrera at U Connecticut, who's working on adding sulfur and chlorine chemistry to our model. So the initial results only focused on the hydrogen chemistry of the atmosphere, but of course on Venus, the sulfur and chlorine is super important. And if we want to reliably model the clouds and understand how those are impacting D to H and escape of hydrogen, we've got to model the sulfur and chlorine as well. So Simon has attacked this work through an REU project that I managed last summer, and he's continued to work with me remotely this academic year. Bless him, photochemistry can be really tedious and difficult, so doing it as an undergrad is very laudable. So very proud of the work that he's done. And we're also working on adding in aerosols so we can start to think about those cloud processes. Meanwhile, I mentioned that there's this dichotomy between the day side and the night side on Venus. This is like several plots to show this. And the point here is that there's very strong winds that go from the day side to the night side, especially across the dusk terminator, leading to a whole bunch of hydrogen that builds up on the night side of the planet compared to the day side. So in order to get at this, we have, we're working on expanding the model to 2D. So Bethan began this work when she was still here, but now that she's moved back home, KP is continuing this work. So the goal is that instead of just having altitude as the vertical coordinate, we will also have solar zenith angle as like the other coordinate. So we can simulate a variety of different conditions throughout the solar day. This will also allow us to model this transport horizontally across the planet, which is not something that people are typically doing in photochemical models. Usually it's just all vertical. So we're excited to see how that goes. So quick summary for Venus. This mechanism HCO plus DR drives about half of H loss today, which changes our assessment of how stable oceans could have been in the past on Venus. And future missions will give us a lot more information to work with that'll help constrain our models, but we do have some remaining gaps concerning the upper atmosphere. And this stuff, I get asked this question all the time when I talk about the Venus, this H escape on Venus. First, people ask me, oh no, should we worry about this on Earth? And the answer is no, probably not, because we're a nitrogen dominated atmosphere. But on other planets that may be CO2 dominated also, definitely we would expect this mechanism to be occurring, especially if there's water in the system. It may also be good that the escape is faster on Venus today for habitability, but that also kind of depends on whether oceans ever condensed on Venus or on potential exovenuses. Okay, so now for the last part of the talk, I'm going to talk broadly about my perspective on exoplanets coming from the solar system background. And if you know Bettridge's law of headlines, this is sort of applicable here. Will the answer be yes or no? Let's find out. Or is it somewhere in the middle? Much more likely. So the way it looks to me, folks who are thinking about the escape of atmospheres on exoplanets, I think have focused a lot on escape of primary atmospheres. Not everyone, but many of the papers are addressing this. So this is as an example from my friend Laura, where she showed that flaring activity of M dwarfs is very effective at removing water equivalent hydrogen from primary atmospheres around super Earths. So there's a lot going on in this plot. I'll try to break it down. She's got stellar mass on the vertical axis, and then each panel is a different size of planet in Earth masses. And then the color bar here is the effective, like, it's terrestrial ocean is the unit here. So like an Earth's amount of water that's been removed. And you can see here in the middle on these planets that are kind of close in Earth to size, this is pretty effective at removing this water. But I'm going to pick on Josh because I know he's here. Other work is showing that, you know, even if you can remove these primary atmospheres, that doesn't mean you've completely lost all of your volatiles. You may still have some species remaining. You may even outgas atmospheres after the primary has been removed. I don't have an example for that, but that is totally possible. I mean, we see evidence of that here on Earth today. It's probably not totally replenishing our atmosphere, but on different planets, like, okay, I was going to call Io a planet. Io is a moon, but I think of it as a planet, right? It is another world where outgassing is very important to the formation of the atmosphere. And that one's very thin, but we may have a similar scenario on other exoplanets out there in the galaxy. And if you can retain these secondary atmospheres, it's kind of a question of what the escape scenario is through these other processes. They may also be vulnerable to all the other escape processes I've talked about and ones I haven't talked about, not just the hydrodynamic escape. Something we've learned from Mars is that we still don't know a lot of stuff. So here is a sort of a schematic of many processes on Mars that have been going on throughout its history from one of my mentors, Bruce Jakosky. I've told him I don't like how the text changes orientation, but the point here is to show there's lots of stuff going on. So the orange bars up here are showing processes that will remove water or hydrogen from the Mars atmosphere. And then the blue ones down here are things that will provide it. And you can see that these things are all going on concurrently. And the timing of when they occurred may matter significantly if we're thinking about other planets. Maybe they're just like Mars, but maybe not. So on Mars, we think there's probably early hydrodynamic outflow to remove an early H envelope. But there's also a lot of catastrophic flooding and volcanism that occurred early on in history, which may have released more water onto the surface. And then escape has been ongoing throughout its history as well. And there may have also been, excuse me, processes that sequestered some of the water of Mars deep into the surface, like never to be revolatilized again. And there's a lot of uncertainty around this now. Although we have studied Mars really well, it's really hard to extrapolate back in time. This is one reason why it's hard to go back in time. The obliquity of Mars varies chaotically over time scales of 20 million years. So on Earth, it's pretty stable. On Mars, the obliquity is also really similar to Earth's right now, giving it like similar Earth-like seasons. But we don't really know how that changes over very long time scales. So the right plot here is a probability distribution of what the obliquity may be over different time scales considered. And since it's chaotic over time scales of like 20 million years, then when you get to 50 million years, 100, a billion years, we really only have this statistical study to rely on. And you can see that even for the shortest time frame and the most peaked distribution, the sort of jaggedy one here, it's still possible to get a huge range of obliquity values, and we don't really know how to predict them, which means we can't predict the climate state that Mars was in 50 million years ago very effectively. We really just have to do a statistical study. And that's very difficult since we only have one Mars to work with in the solar system. But it's important because, as these other plots on the left show, when you have a planet with a very high obliquity, that can mobilize a lot of water that may be available in the ice phase or the liquid phase into the atmosphere. These are by Wan-Ying Kong out of, I think, Harvard. So it would be great if we could understand how to model these things, because that can really change your climate cycles and your circulation around the planet, but it's very difficult to do. So a little point of comparison as we get closer to wrapping up here. The solar system is great. We can send missions to these planets and use them as proxies for other exoplanets. But we have a limited number of these planets available, and there are a limited number of planets in the solar system that even have atmospheres. So it's very hard to extrapolate back in time or make statements about population level behavior. Benefit is that we do have our models relatively constrained, compared to, those for exoplanets, but again, it depends on the planet. Mars has received lots of attention, Venus less so, and then like, let's not even get started on the outer solar system, you know? We should definitely send a Uranus probe. I'm all for it. Go to all planets. As far as rocky exoplanets, the technology is really the limitation, right? They're far away. They're hard to see. So that's still really becoming more possible in the present day. There was recently this first detection of photochemical products on an exoplanet, which was very exciting. Of course, for me, I was like, well, of course there is. Like, you've got an atmosphere, you can do some photochemistry. But it's great that we were finally able to detect it positively. The benefit here is that on the exoplanet side of things, we have numbers on our side. We can look at a lot of different planets at different points in their history and use those to provide comparisons or maybe serve as a proxy for what might have happened in the past at Mars and Venus or other solar system planets, for which it's hard to extrapolate. And like I said, it's relatively unconstrained in our models since we have fewer data points to work with. So it will be great if we can use these solar system planets in a way to constrain the exoplanet models, but that kind of involves like exploring the parameter space because it's so unclear what may actually be happening on these rocky worlds. So while we are waiting for telescopes to advance, we should definitely work on improving our models. I started as a modeler, so I'm very much in favor of this. I hope you enjoyed the meme, just to wrap us up. I think we have a good opportunity to continue developing like model collaborations. I think a lot of us who have done photochemistry don't like spend a lot of time thinking about what happens when you send parts of your atmosphere down to the surface. It's sort of just like a little sink for us. But, you know, as I said in the beginning, atmospheres shape the surface and surfaces shape the atmosphere. So there's opportunity there to think more in depth about that. I think it would also be great to try to connect different models of atmospheric loss. So loss of primary atmospheres, loss of secondary atmospheres, and when each of those are formed in comparison to one another. Like, does the secondary atmosphere have to form at the same time as the primary, or can it form quite a bit later and then maintain its presence on the planet? It's difficult, of course, because all of these different models that think about different kinds of escape and different kinds of atmospheres are kind of working in different spaces. And if you try to combine them all into one, you run the risk of like making a black box that it's hard to tease out each part. So I think we have to think really carefully about how we link these together. And what the limitations of each are and how they can sort of complement each other. I didn't really mention the model types, but there's all kinds, in addition to photochemistry, there's also like particle transport types, which are better for thinking about some aspects of non-thermal escape. And of course, the like geochemical models will get us closer to understanding that surface to atmosphere connection, which are not currently done super well in like atmospheric photochemistry models. And then speaking as a photochemical modeler myself, like the star-planet interaction is pretty simple. I don't have a lot of different ways to capture stellar activity right now, but I think that's definitely an opportunity for improvement, at least for mine. Many people do have different aspects of stellar activity in their models, but we're not all working on the same footing. So lots of opportunity, lots of things to do. I've got some final summary points, which is everything I've just said. And I'll just wrap it there and happy to take your questions. Yeah, I'm a big Star Trek fan. Sorry about all the references. Also not sorry. Yeah.
Hi, thanks for the great talk. I had a question about the water being really high in Mars's atmosphere. I was wondering if you have any suggested mechanism for how the water gets that high during the dusty season. Is it that dust is actually like being lofted into the like that high up into the atmosphere and is carrying water with it? Or is there some other mechanism at play that brings that water up there?
Thanks for this question. Sorry, I ran over this explanation because I was concerned about staying within time. So the way that it works is as the dust gets into the atmosphere, it tends to induce warming because it's just increasing the optical depth. So the radiation can get in, it's hard to get out again. So it just warms the atmosphere, which raises that level at which the water vapor will condense out into ice. We don't really go through the liquid phase on Mars, but it will just go straight from vapor to ice, which I think is called deposition officially, even though it's not on a surface. Whether the dust is actually carrying water is an interesting question. I think yes, there's been like some work done on this. And I actually had ideas for a similar project that I proposed to Bruce because he's my like closest geology dust type expert person. He had been working on it with a student, looking at how effectively that water can adsorb onto the dust particles. So that student got some nice results showing that if you adsorb water onto a dust particle and then loft it up like 30 kilometers, it'll desorb that water and change the water column by about 10%. But he didn't think that it was worth doing the updated project that I suggested because he said he thought through this whole thing and you could actually just do the whole thing analytically. So bummer for that. But I think, yes, that dust absorption has some effect. One other thing I want to say about that, it may also have a big effect on the D to H ratio because I mentioned briefly this fractionation factor of like how differently D and H escape, but there's like fractionation factors for every process out there. So there's also a fractionation factor for water adsorption onto dust grains. So this fractionation factor, usually we give it in like a percent. And for Mars, the escape is like, the D escape is about 4% as effective as the H because of the mass difference. That correlates to a number of 0.04. The fractionation of water vapor, like different, like HDO versus H2O onto dust grains, the fractionation factor is 2. So that's enormous, or it might be more like 1 point something, but it's much, much larger. So I think there could be definitely something going on there, but I'm not aware of a lot of updated work that's been done on it. Sorry for that really long answer, but I hope it was helpful.
So is HD as heavy water easier to absorb or harder to absorb?
Easier, yeah.
Okay, so,
Yeah.
okay, I'll think about
And
that.
technically that is semi-heavy water and heavy water is D2O.
Mhm.
It's actually harder to find info about HDO in literature than heavy water. Also, don't drink this stuff. It's not good to drink it.
There's a question on Zoom. Woody,
Thank
do you wanna unmute yourself and ask their question?
Yeah, Woody Sullivan here. It's very, very nice talk in terms of us non-experts and all the different processes and such. And of course, it all went very fast. But to look at Mars, can you combine it, your work, along with the pressure that you expect profile and such, to talk about what kind of liquid water there might have been on the surface and have your new results affected that if you look at different times in the past?
So are you thinking about like calculating like the amount of water due to phase changes under different climate scenarios?
Yes, and you're looking at the loss of the water. So at some stage you can't have any liquid water at all. But this might be combined with, the geological results, obviously, that have some interesting results on that issue.
Yeah, so you definitely could do that with the photochemical model. You just need to give it the right conditions. I think the difficulty is just identifying what those conditions are. Like I was discussing, the obliquity variations make it tricky. We could do this back to about 20 million years. I haven't done it myself, but it's definitely possible. You would need to add some additional chemistry to the model that I don't have in there right now, but one could, in theory, do that, yeah.
Yeah, no, I can see the obliquity results are really putting a huge uncertainty in all this.
Yeah, thank you for the question.
Great talk. I actually have a question following on from Andrew's, which is, if I understood your answer correctly, you said the height of the cold trap essentially increases with the dust storm. So does that also, how much does that reshape the atmosphere as a whole? Is it changing essentially the whole height of the atmosphere, or is it just changing the like ratio of the various components? Like, is the thermosphere shrinking because that cold trap is getting pushed up?
Yeah, good question. It kind of, excuse me. So anytime there's heating going on, it does have this effect of sort of, we call it puffing up the atmosphere. So, for one consistent density, you might see that the density of whatever that species is, like CO2, occur at a higher altitude. So it does sort of change the general shape of it, but it doesn't necessarily shrink the thermosphere completely. And yeah, I think that's what I would like to say about that. Yeah, because all of these parts are related to some extent, but also somewhat independent. So changing like the altitude at which the water is going to condense out does not necessarily directly affect all of the other features of the atmosphere, but it does change the chemistry, which then can have knock-on effects. Yeah. Oh gosh, I don't know who was next. I think over here in the red jacket.
No.
I think you've been having.
Yeah, I have a quick question. People talking about an ocean worth of water in the upper mountain. Yeah, and what does a hidden water supply like that do for something like Venus? Or also particularly for planetary M stars, which have been stripped off early in the history of the star, but still have this treasure of water in the mantle.
Okay, I think I missed a key word earlier in your question, but I think I understand what you're asking. So how does water that's under the or in the interior affect this loss, right?
Yeah, I mean, because if you do something terrible with the surface, you still got this water in the mantle.
Yeah,
And there are ways, especially for an M star, you've got 1 trillion years to get it back out.
yeah. Yeah, and the geological processes are ones that I'm interested in, but not super expert in. My understanding of the mantle, at least on Mars, is that water is probably pretty well trapped there. After the past theoretical magma ocean solidified. So it's probably not easily able to exchange with the water on the surface or in the atmosphere. It's easier to do so if you have a secret water cache in like the crust. That's a lot more able to be disrupted. However, if you have a lot of volcanism going on that's reaching down into the mantle, then you may be able to like reach that water and what's the word I want to say? Just bring it out onto the surface. So we do have this question on Mars of has there just been a steady loss of water and a steady increase in D to H over time, or was that D to H ever reset? Because if you think that the water that Mars was formed with has a similar D to H ratio as Earth, that means that if there's this water locked up in the interior and then eventually it does come out via volcanism, you might have reset that D to H ratio if you throw out enough water onto the surface. We really don't know the answer to that question, but we expect that would change the assessment of how much water was lost, because that might be sort of hiding from us the details of what happened, because we're using this one D to H number to understand the loss. Hopefully that makes some amount of sense. But there's also reservoirs in the mantle that may not be tapped at all, and they may maintain that like original water that it was formed with. There is a paper from Mars that suggests that there may be multiple different reservoirs inside the mantle of Mars that have different D to H ratios. And I've looked at that paper a couple times and just, I should probably look at it again, because when I first read it, I didn't understand it completely due to my like lack of geological knowledge. Okay, Josh, then Trent, then, okay.
Yeah, I'm just curious, could you perhaps give me a better intuition for like how does the ways in which bulk atmosphere affects the HCO associated with recombination loss rate? You kind of alluded to the fact that like a more nitrogen dominated atmosphere would have a lower influx, but
yes,
how does like 100 bar CO2 and a bar CO2? Just thinking of Venus did go through a hell of a time and bulk atmosphere
Right.
changed considerably. Would the flux change? Is it just diffusion limited?
okay, I think there's a lot of questions in here. So, no, that's fair. And I sort of glossed over this thing about the terminal ion. But so every molecule has something called a proton affinity, which is just its tendency to grab up a free proton or NH plus. So on Mars, CO and H2O are the most likely molecules that like to grab a proton. So they will form HCO plus or H3O plus. But the neutral water molecule is again mostly down in the lower atmosphere, whereas the CO is sort of extended through the whole thing. So that's why it really tends to form the HCO plus preferentially, which then leads to this whole hydrogen loss process. I think that if you change the pressure of CO2 it wouldn't necessarily change like that chemistry, that chemical tendency. But you may get other effects that are happening through chemistry or diffusion that would make it harder for the water to like. Or rather, that would maybe change like which molecule is more likely to grab up those protons. It depends on where they're produced and lost. So there, I'm just gonna say, yeah, both. I guess there would be some effect, and I don't know exactly what it would be. And then I can't remember the last part of your question, or did I cover it all sufficiently?
We can chat more. later.
Okay, great. Okay,
My question is really related. I was gonna wonder how the H2O plus, especially recombination changes under, the changing solar flux back in time, like under like higher EUV conditions.
Mhm.
You know, back in Venus's history, cause yeah, I have no idea about that.
we have a paper draft about this sort of that I've been working on with Bruce and others, so that will come out. I think we're trying to like integrate a whole lot of thought about this into one big review paper. So there's like the question of how it changes back in the past with greater EUV activity, and you can also think about how it changes in the current day just with the solar cycle. With the solar cycle in the present day, as you go towards solar maximum, there's actually less non-thermal escape. So it kind of, this HCO plus mechanism is less important, but that's really just because the thermal escape is so much more efficient. And also maybe because the atmosphere is sort of puffing up, so you've got more stuff higher up that will absorb the radiation before it comes and drives all the other chemistry. Back in time with EUV, so with higher EUV, you should get more dissociation of water. But again, there may be like greater absorption of it before it reaches the altitudes it needs to drive that dissociation. This is, we have been going around in circles on this ourselves and trying to figure it out. So it's a really good question. And we're working with Ed Tiemann, who is also on the MAVEN team and is part of the EUVM instrument, which monitors the EUV emissions from the sun to sort of get at how this would change. There are a variety of papers that have thought about this and the effects on like oxygen chemistry, for example. So I'm like visualizing this plot in my mind, but you can't see that because it's in my brain. I'm trying to remember who wrote it. I think it was a Chespier paper, or it might have been Rebus et al. But basically showing that as you go back in time, the EUV goes up, and so does the like oxygen dissociative recombination and various other like oxygen-based processes. But I don't think anyone has made that thought for HCO plus yet. Okay, and then
Yes,
one more.
my question is also about HCO recombination, so, but it's about Earth. So on Haitian Earth or like Archean Earth, the atmosphere is also CO2 rich or potentially CO2 dominant. So I'm just thinking about like, can you say something about the implications of now we are discovering these reactions for like the implication for these reactions for the atmospheric evolutions of Earth? Does it change it a lot, or like is it still the same?
And admittedly, I know a lot less about Earth and especially Archean Earth. But if you had a greater amount of CO2 and CO available in that scenario and sufficient water, then you may see some of the same behavior. I imagine it would. I guess it depends on how much water is available, because like I was saying in the answer to a different question, the water molecule actually has a much higher proton affinity than CO, so that may actually end up grabbing up a lot of those protons. I guess it depends on where the CO molecules and the water molecules are in the atmosphere and where the protons are. I think typically you'll get the protons being produced higher up in the ionosphere, so it may still be the same if you see the same sort of like species profiles that you would expect with the water mostly down below under the cold trap and the CO wherever it wants to be. I haven't thought about like the escape from early Earth and whether that would be a significant channel of H loss, but we do have a lot of water on Earth still, so presumably not, unless we had even more in the past. Good question. Yeah, worth thinking about.
We're past the hour, so we better wrap it up. I did want to make a quick plug. If you'd like to join us for dinner, we're going to go to Agua Verde, so just come on, let me know. Let's thank Eryn again.